The other thing we're interested in besides the energies are the probability distributions. So let's look at our trial functions here with the probability distribution. So if we plot psi star psi, along the axis, so we have our nucleus A and nucleus B here. This will kind of look very similar to what we were looking at before in terms of the wave functions adding together, but we'll get something that increases, decreases a little bit, but there is probability between the two nuclei. And this is what we know as a bonding orbital. Right, so we get electron density between the nuclei. And this is what is holding this molecule together, why we get that negative energy that we saw with the potential energy diagram. And again, this is psi plus here. We can look at a similar plot for psi minus, where we're looking at the probability distribution. And we'll have our two nuclei represented by these dots here. And so we'll see a sharp increase here. But the difference we'll see here is this comes down and forms a node. Right, so we have a region between where there's zero probability and there's a node between our nuclei. Let me just move this so you can see that. And this type of orbital is what we know as an antibonding orbital. And we call this antibonding because we get that region between the two nuclei where we have this node, right? We have a node where there's not electron density between the nuclei. That's not going to hold them together. And so the nuclei are more exposed to each other, and they're going to want to push each other apart and break the molecule apart. And so it's against bonding. It's an anti-bonding orbital. Another way this is often drawn, a sort of pictorial way I like to represent it, is for a bonding orbital, we could say we have our two 1s orbitals that are spheres, and we're going to add and subtract them. Right? If we add them together, we'll get something that sort of combines these two spherical objects into sort of an oblong object. And this is our bonding orbital. And we label this as a sigma orbital. And we'll get into what that means specifically in just a second. And if we subtract them, let me give myself space here, we get something that looks like this, where we have a node in the middle that's a plane. One's positive, one side's negative, with our node in the middle. And this is also a sigma, but this is a sigma, I have to write the sigma star. Keep drawing where my face is. A sigma star orbital, or an anti-bonding orbital. Now, just to get into some of this terminology here, right? So the same sort of thing is going to happen with H2. We're going to end up with a bonding and anti-bonding orbital. The difference with H2 is that now we have 2 electrons that would go in the bonding orbital and 0 electrons in the anti-bonding orbital. So what does sigma mean in this context? So this is going to follow the same sort of SPDF orbital. When we talked about multi-electron atoms, right? So this is for atoms. When we talked about multi-electron atoms, these became capital letters, capital S, capital P, capital D, capital F. And now as we move to molecules, and I'll be specific here, this is diatomic molecules that we use this terminology for, we start using Greek letters. Lowercase sigma, lowercase pi, lowercase delta, and you don't really ever usually get beyond delta. But there are, I guess it would be phi. I'm not even sure, so don't quote me on that one. But for sure, sigma, pi, and delta orbitals are things that are seen. What do these mean? These kind of follow the similar sort of thing as our atomic orbitals, where a sigma orbital has no nodes in the plane of the bond. Sorry about that notification ding. right? So even our anti-bonding orbital, if we're looking in the plane of the bond, so our bond is along this plane here, there's not a node along that plane. A pi orbital has one node along the plane of the bond. A delta orbital has two, and a phi orbital, or whatever the proper Greek letter that you would use, would have three. And so we'll look at those, what those look like shortly. And so if we want to write an electron configuration, say we're looking at say an H2 molecule, we didn't solve this exact problem, but it looks very similar to the H2 plus, where we get a bonding and anti-bonding orbital. Our electron configuration, we can write similar to how we would an atomic configuration. We would say that we have this 1s sigma bonding orbital that has 2 electrons in it, just like we do with atoms.